Okay, so hi everyone. Today we'll be studying light. Alright, there are various topics to it: the reflection, refraction. Light is a chapter that will be with you throughout your life. Alright, it is an applied science, you can see it everywhere. What do I mean by light? Not just light that you see as a tube light or bulbs or anything. No, we'll be going more in depth. When we see a bulb, alright, what do we see? There is light rays coming out of it. Alright, these are all rays. A lot of rays of light make a beam of light. Alright, light is everywhere. We need light to see stuff, to write stuff, to do things. We need light. Where do we get a major light? What is a major light source? It's the sun. It is the source of all life on earth. Alright, light is very important. And the various things that happen with light in our life around us is very interesting, and let's get into it. So the first topic is reflection of light. Alright, reflection of light is bouncing back of light rays when they strike a surface. Alright, it follows certain principles and involves the following terms. What is reflection? You can see over here a smooth surface. It bounces, the key word over here is bounces light. Reflects light. Okay, it is reflecting light. Here we can see light rays. In the picture we can see light rays. Alright, what is happening? Light is coming over here, it is getting reflected. This is basic reflection of light. Okay, what is reflection? Bouncing back of light rays when they strike a surface. Okay, a smooth surface, more bouncing, more reflection. Incident ray. Okay, the ray of light that is coming first, okay, which is falling on the surface, it's incident ray. Okay, and the one that is bouncing off is reflected ray. Okay, remember that. The ray of light that strikes the surface, the ray of light that bounces off the surface. Okay, it is a surface, this is incident ray, it touches it, it is bounced back. Point of incidence, the point where the incident ray strikes the surface. Can you see this point? This is point of incidence. It is touching the surface over here, it is point of incidence. What is normal? A line perpendicular to the surface at the point of incidence. If I take, this is the surface, this is my incident ray, it touches over here, point of incidence, and it is reflected over here. If I draw a perpendicular line, what is perpendicular? At 90 degrees. Okay, if I draw a perpendicular line, a straight line, falling imaginary line, this is called normal. Okay, why do we do this? So that we can find at which angle this light is coming and at which angle this light is going. Okay, it is coming over here, it is going over here. We draw normal. Okay, angle of incidence, it is the angle that this incident ray makes with the normal. Okay, makes with the normal. This highlighted angle is the angle of incidence, I. Okay, and this angle of reflection, angle R. Okay, the angle between reflected ray and the normal is angle of reflection. Angle between the incident ray and the normal ray, it's angle of incidence. Alright, let's move on. Laws of reflection, this is very important. What are the laws of reflection? The incident ray, reflected ray, and normal to the surface at the point of incidence will all lie on the same plane. Now, this is the plane, this is the light falling, this is the light bouncing off. This light, this point, this ray, all will touch this plane, all will touch this surface. Okay, all three, the incident ray, the reflected ray, and the normal is this one, sorry, yeah, this one. This will all touch the plane, all lie on the same plane. Okay, the angle of incidence is equal to angle of reflection. Alright, this is an important point. normal, falling, bouncing, okay, falling, bouncing. This angle that is made with normal is equal to this, I, R. I is equal to R. These two angles are equal. Now we come on to a basic application of reflection, that is mirrors. Okay, so for a mirror, plane mirror, spherical mirror, we have two spherical mirrors, one plane mirror. Plane, as the name suggests, it's plane, it is not curved. Plane mirror. You can see this girl seeing in a plane mirror. Okay, we have plane mirrors in our houses, on our almiras, to change. Whenever we see in a mirror, we see a clear picture of ourselves. The picture that is shown will be determined by the mirror, and I can tell you by the mirror what type of image will be shown on the mirror. Okay, so what are the uses of a plane mirror? Reflection, personal grooming. All right, if you see someone putting makeup on this and they use a plane mirror because it shows the exact replica of your face. Okay, surveillance, etc. Properties of the plane mirror, it will show you a virtual image. Now what is the virtual image? All right, virtual is not real. Okay, the image formed will be behind the mirror. Okay, you will see it over here, but it is at a distance. Okay, can you see this girl? She's at a distance from the mirror, and that same distance is shown in that mirror. Okay, this is a virtual image. Image will be same size. Okay, same size and laterally inverted. Image will be same size and laterally inverted. Okay, image formed by the plane mirror, virtual, erect and laterally inverted. Okay, laterally inverted means right will be shown as left. Okay, laterally inverted. Erect means straight, upright, straight standing. Okay, same size means whatever size she is over here will be shown over here. Face is not small, body is not small or large. Okay, this is the properties of a plane mirror. A spherical mirror. What is a spherical mirror? It is curved. Over here you can see this plane mirror, light will come, fall off. Okay, but in a spherical mirror there is a little bit of bending for reflection. Okay, I'll tell you how. There are two types of spherical mirrors. Okay, one is concave mirror, one is convex mirror. Shape of the concave mirror, okay, it is bent inside. If you've seen those parking mirrors, all right, that is a convex mirror, but it is shaped outwards. Okay, you see something strange about this mirror? It is bent outwards. Okay, it is reflecting. Okay, but it is bent outwards. This is convex. Bent inwards. Okay, concave. Okay, inside of a spoon, inside the spoon is concave. Okay, it is bent like this. Okay, I'll show you. It is bent like this. Okay, light falling from this has a bent inside surface, but of light falling from this has a bulging out surface, that is convex. Okay, so spoon has convex and concave. Where do we use concave mirrors? The uses are important. Used in reflecting telescopes, shaving mirrors, etc. Where do we use convex mirrors? Okay, convex. Okay, convex. Used in rear view mirrors. Okay, it is used in rear view mirrors of your car. Why? It shows a smaller image. Okay, a bigger image. Okay, whenever you see your car rear view mirror, it would be side view mirror, it would be written objects in the mirror are closer than they appear. Why? It shows a bigger image and in smaller size. Okay, security mirrors, etc., parking mirrors, all use convex mirrors. Refraction of light. Refraction is the bending of light. Okay, Reflection is bouncing. Refraction is bending. Okay, I'm not just totally reflecting this. Okay, I'm just slightly bending this way, or slightly bending this way. Okay, the light is coming over here, going like this. This is reflection. This is refraction, just bending. If you were going straight, I would just bend you over this way. Okay, this is refraction. When will it bend? After striking a surface, and I will tell you what happens. Refraction is the bending of light when it passes from one medium to another. Okay, supposedly here it was air, here it is water. As soon as this light ray will strike the surface of the water, it will bend. Okay, it will bend, it will not, it means that it will not go in a straight fashion like it was going in the same direction. It will bend. Okay, it will change direction. Why does this happen? Because the speed of light is different in different mediums. All right, light is traveling with a different speed over here, with a different velocity. Okay, but here its velocity will change. It has direction, it will change direction. Okay, remember that. And what makes this change, we'll study further. What are the laws of refraction? The incident ray, refracted ray, and the normal to the surface at the point of incidence all lie on the same plane. So simply, as we remember, coming over here, bending, this point, the normal, okay, normal, incident ray, refracted ray, all lie on the same surface. Okay, same plane. Ratio of sine of angle of incidence to sine of angle of refraction is constant. Okay, and this is known as refractive index. Refractive index. What I mean by this is sine of angle I divided by sine of angle of refraction, not reflection, refraction. Okay, if you've studied sine, cosine, tan, theta, taking the sine of this angle, taking the sine of this angle, what were these angles? Okay, if you remember in reflection as well, angle of incidence, angle of reflection. Here it will be angle of incidence and angle of refraction. Okay, this is equal to Ri. What is it? Refractive index. Refractive index is something that helps us to get an idea of how much will be the bending of light rays when entering that medium. If I say the refractive index of water is 1.33, okay, means the bending will be this much. Okay, the bend. Now we move on to atmospheric refraction. What is atmospheric refraction? You see stars twinkling. All right, if we go about, let's take over here. Okay, this is the earth, this is the earth. Here it has atmosphere, here it has stars. Okay, a person over here on the earth, okay, he will see stars, okay, but it will appear to him twinkling. Why will it appear? Because the light rays that are coming from the star will go through this atmosphere, okay, and they will bend. They will constantly bend, okay, while coming to our eyes. Okay, while coming to our eyes, they will be constantly bending. That would appear as twinkling. Okay, that is atmospheric refraction. The bending of light as it passes through Earth's atmosphere. Atmosphere is a different medium. Alright, it has a lot of chemicals, gases and all. It will bend light as differently as compared to air. Alright, we have air, but atmosphere has a lot of gases. So the bending of light as it passes through Earth's atmosphere is responsible for various optical phenomena like sunrise, sunset, twinkling, etc. Okay, the sun appears more red. All right, that is also due to refraction. We will come into it when we study dispersion and scattering of lights in the next slide. Another application of refraction is total internal reflection of light. Total internal reflection occurs when light passes from a denser medium to a rarer medium. Okay, what is a denser medium? Solid, a solid. What is a rarer medium? Water. Rarer means lighter, less dense. Okay. When light passes from a solid denser medium to a rarer medium at an angle of incidence greater than a critical angle, it is total internal reflection. Alright. Now we come to the critical angle. What is the critical angle? The minimum angle of incidence that allows for total internal reflection, angle of incidence and reflection, the angles at which light strikes and reflects within the denser medium. Okay, supposedly I'll tell you where critical angle. Okay, supposedly there is a diamond. Okay, light is entering from a rarer medium to a denser medium. It is a solid. Okay, the angle of incidence, okay, is greater than critical angle. Okay, the angle of incidence is greater than critical angle. Okay, or it might be less than critical angle. Alright, so when the ray of light will fall over here, okay, angle of incidence, it is greater than the critical angle in a diamond. Always remember, angle of incidence is greater than a critical angle in a diamond. Thus it will go total internal reflection. This is important. Alright, I'll show you in a better diagram. Okay, over here, see, angle of incidence that it is coming at and it is bended, it is more than this angle, critical angle. Thus this light ray will go multiple reflections, okay, inside it. It is coming from a rarer medium to a denser medium, then it will be going from a denser to a rarer medium again. What is it? Air. Okay, it will go back to air. Thus it appears very sparkling to us. A lot of reflection goes in a diamond. Okay, now some events of refraction. All right, refraction also leads to twinkling of stars. A stick dipped in water, let me show you. Supposedly it's a pencil. Okay, the pencil is going over here like this. This is a pen or a pencil, but it will appear to you, when you see it from over here, it will appear to you somewhat like this. Okay, somewhat like this. It will appear to you when you see from your eyes. Okay, why does this happen? Okay, because light coming from this way, okay, it is getting bended inside. So the image formed by your eye is also getting bended. Alright. So a stick dipped in water appears to be short or bent. See, in a swimming pool, the depth of the swimming pool appears as if it's not that deep, but when you go inside it will be 10 feet. Alright. So this is what refraction does. Alright. Twinkling of stars, I have told you. Multiple images found by a thick plane mirror, this is also an event of refraction. Alright. Other events include like the red of sunset. This is also due to refraction. I will tell you how after dispersion. Alright. Refractive index, like I told you, it is sine of angle I divided by sine of angle of refraction, but it is also called velocity of light in air divided by the velocity of light in other medium. We always take with respect to air in the numerator, velocity of light in other medium. Supposedly we need the refractive index of water. So what we would have done, velocity of air, of light in air, okay, divided by velocity of light in water. Alright, velocity of light in water. this division will lead to 1.33. Okay, and similarly for glass, air divided by glass, it would lead to 1.50. Okay, the details are not that important for you right now. Scattering of light. What is scattering of light? This light that we know na, alright, I'll show you in a different diagram. See over here, this light that we know, okay, it can break off into different colors, different bands. All right, scattering, it has a tendency to scatter when it hits a surface like this. What are the conditions? Scattering of light refers to the random redirection of light rays in different direction when they interact with particles or irregularities in a medium. Some materials, some surfaces, they disrupt the light that is falling on them. Alright, it will send it in different directions, different speeds. Alright, this is called scattering of light. Have you seen a rainbow? Alright, when sun rays, alright, coming from the sun, they go through the water that is inside the atmosphere, it is suspended, the water droplets. These droplets will disrupt this white light into different colors. Alright, let's see over here. This is a prism. This is a glass prism. Alright, glass has a different refractive index as compared to air. Maybe there's air over here, and the white light is going like this, and this prism breaks this white light into a band of different colors that we know as Vibgyor. Okay, 7 colors. This is what makes our world beautiful, colorful. Alright, what is dispersion of white light? Dispersion of light refers to separation of white light into constituent colors when it passes through a prism or other mediums. It forms a spectrum of colors ranging from violet to red. V to R. Okay, it goes from V to R. Alright. Now, what is a lens? We come back to lenses. Alright, we know mirrors. Okay, mirrors is now done. But there are also other refractive substances called lenses. Alright, there are two types of lenses, like there were two types of spherical mirrors: convex lens, concave lens. A convex lens looks like this. Concave lens, convex lens is thicker over middle and it is narrower at the edges. A concave mirror is thicker at the end points and thin at the middle. Alright. These lenses are used to correct your visions. They are used in cameras. Your phone might have a convex lens, concave lens, microscopes. All use lenses. We don't use mirrors because we need a different type of image. Have you seen a magnifying glass? A magnifying glass, it shows a bigger image. How does it do that? It has a lens, not a mirror. Okay. Convex lens, thicker at the center, converges light rays. What do you mean by converges light rays? When light rays will pass through this, they will bend to a particular converging point. Converge. Alright. This is used in magnifying glasses, cameras, etc. And concave lens, thinner at the center. Alright, this is thin. Divergent rays. What does this do? Sorry. Goes like this, goes like this. Light rays coming. It strikes this and it goes like this, diverging in different directions and whatnot. Okay. Convex, converge. Concave, diverge. Okay. Now, what is the power of a lens? You all must have specs, alright? Or most of you might have specs, or your friend has specs, or someone in your family has specs. What is in that specs? Lens. Okay. Why is that lens being used? Because to correct your vision. Okay, I'll show you. This lens has a power. Ask anyone with a spectacles, what is their power? The power of a lens is measured in diopters. All right, diopters. The unit is D, and it is given by the formula P is equal to 1 upon F. What is F? Focal length. Okay, this formula is important. P is equal to 1 upon F, where P represents the power and F represents the focal length of the lens. Okay, supposedly you have specs of 5 diopters. What does that means? 5D. Okay, that means is equal to 1 upon F. You take 100 centimeter and the focal length of your lens, supposedly it's 20, will come out to 5. This will be a power. We convert the focal length in meters, which is already given in meters, to centimeters. So we multiply all by 100, and this is 100 upon the focal length in centimeter, which will give you the power. Okay, but focal length is always in meters. We convert it to centimeters. So power is what? 1 upon F. Remember the SI unit, it is diopters. Okay, D, diopters. I'm repeating, diopters. Uses of lens: correcting visions, cameras, microscopes. Now the human eye. It would be interesting for you to know that there is a lens, okay, a convex lens, a concave lens, a lens of this sort in our eye as well. Okay, you can see it over here. It is written lens. See the lens. Okay, the power of accommodation of an eye. The ability of the eye, our human eye, to focus on objects at different distances by adjusting to the shape of the lens. All right, our eye is the biggest camera, the most defined or most professional camera ever made or ever will be made. All right, our eyes can focus on an object that is near or far away. Okay, how does it do that? These are some muscles. Okay, muscles to adjust the lens. Okay, it can adjust the focal length. Okay, these muscles help adjust the focal length, and in turn it adjusts the power. Okay, this is called power of accommodation of the eye. Okay, it is an important term. Power of accommodation of the eye. The ability of the eye to focus on objects at different distances by adjusting the shape of the lens. It adjusts the shape, it adjusts the focal length adjusted, power adjusted. All right, people who wear specs, these muscles are weak. All right, these muscles are weak, so you're not able to adjust easily. All right, that's where you need a correction lens, that is specs. All right, defects of vision. Now there are various defects of vision. All right, myopia, nearsightedness. Okay, difficulty in seeing distant objects clearly. You can see something placed near to you, but far, no. This is myopia. Okay, hypermetropia, farsightedness. Okay, difficulty in seeing nearby objects clearly. My mother has hypermetropia. All right, she can't see something written in a book that is placed close to her. Okay, placed close to her, but as soon as I increase the distance, she is able to see. This is hypermetropia. Farsightedness. Farsighted, I can see far. Nearsighted, myopia, I can see near. All right. Astigmatism. All right. Blurred vision caused by irregularity shaped cornea or lens. You remember this lens that I was talking about? If its shape is irregular, you will see blur. Okay, this is astigmatism. All right, this is a picture of specs or lens correcting vision. All right, hypermetropia. Okay, this lens can my lens would enable me to see far but not near. All right, the image will be found far behind the retina. Okay, Now to correct this, I use a convex lens. Alright. So lenses correct vision. Presbyopia, loss of near vision due to age. With old age, the muscles of the eye that adjust the lens, they become weak. Alright. This is presbyopia, loss of near vision. You can't see nearby. Okay. Sometimes you've seen old people, they can't see nearby properly. Alright. This is due to age. Cataract, clouding of eye lens leading to vision impairment. We see the eye. Okay. This is the eye. In cataract, this part would become very cloudy with blue or a different color. Alright. Okay. It will become cloudy. It won't be able to see properly. This will lead to blindness. Mostly in old ages this happens and people get cataract surgery to fix this. Right? It is fixable. Optical instruments. We use light in optical instruments. We use lenses for this. Alright, we use lenses. Telescope. What is a telescope? Used for viewing distant objects in space, consisting of a combination of lenses and mirrors. You see this tube? Alright. It will have a lot of lenses inside it. That will increase the image that is coming from far. Okay. We can see stars, we can see planets from this telescope. Okay. You can see over here. Periscope. Now, I'm sure you've all seen a submarine. Okay. A submarine, submersible. Okay. The person sitting inside the submarine is able to see outside. How does this happen? Okay. So if you go into this instrument, like it's shown over here, okay, a person putting his eye inside over here can see outside objects clearly because light coming from outside is bended in such a way that there is a clear image formed where the person is standing. This is a periscope used for observing objects from a concealed position. Alright, I may be in a concealed position, I may be hidden, but I can see. Why? Due to reflection. And periscope uses mirrors, not lenses. A kaleidoscope, an instrument that uses multiple mirrors and colored objects to create symmetrical patterns. Here is a kaleidoscope. If you've seen inside a kaleidoscope, it is a hexagonal type of, it's placed mirrors. There is a small image and it's a beautiful pattern like this. Alright, this is used in kaleidoscoping. Okay, so that will be all for light. Thank you.